So, if you recall our last lecture, that given a dynamic system x dot is equal to f of f function of x t u t d t t, and subject to performing index or cost function is like this way. So, first term of the cost function is a terminal cost function, and second part of this one is integral cost function. Then how we have solved this problem? Then first we have generated or formed a Hamiltonian matrix, this is the Hamiltonian matrix, with the knowledge of integrand of the integral cost function, this one, plus that lambda transpose of t of f of t, this is the function of f of t. Behind this idea is, this is the constraint optimization problem is converted into a unconstrained optimization problem using what is called Lagrange multiplier, and Lagrange function is now expressed in Hamiltonian function, and ultimately we got some necessary condition and boundary condition to solve this problem. So, our first step in during this process, our first step is del h del u assigned to a 0, that is the one necessary condition. Then we have a del h del lambda is equal to x dot, which is called the state equation. This is another necessary condition, and del h del x partial differential of s with respect to x is equal to minus del lambda dot star is a called co-state vector, because dimension of this one and dimension of x and lambda are same, and their expression is exactly same. And in place of lambda you replace by x, and that x dot is replaced by lambda dot with preceded with minus sign, and this is the boundary condition we got it. So, one has to solve this equation necessary condition along with the boundary condition to get the optimal solution of our control input, which in turn it will give you the optimal trajectory of our state, and hence it will minimize or maximize the what is called performing index, that we have to check it with considering the sufficient condition, and we have established the sufficient condition for the functional should be a cost function should be a minimize or maximize. This is the matrix. We have to form this matrix, which if it is greater than 0, that j, which is our performing index, is minimum. If it is less than 0, that means less than 0 means it is a negative definite matrix, and this matrix has a dimension n plus m into n plus m. If it is a negative definite, then j is will get it maximum, that means performing index value is maximum. So, there are different situation is we have discussed. First case is fixed final time and fixed final state. So, their first three equation, then del h del u is equal to 0, del h del x is equal to minus lambda dot of x, then lambda dot of t, then del h del lambda is equal to x dot. These three equations to solve, only changes is boundary conditions, and since both are fixed, time is fixed, final time is fixed and final state is fixed, then our delta T f boundary condition delta T f is 0, delta x f is 0. So, there is no boundary condition for that one. Agree? So, free final time, this time free final time and fixed final state, that means delta T f is free. Agree? Delta T f is free, that means we have to make delta T f is free, this equal to boundary condition, this equal to 0, but delta x f is fixed, the final time is fixed by final time, final state is fixed. Agree? So, this is equal to 0. So, only we have a case B, we have only one condition is their boundary condition. Similarly, final time is fixed, final state is free, final state is free. So, delta f is fixed means d 0. So, delta x f is free, that means this boundary condition this equal to assigned to 0, and you have to solve. When both are free, then this equal to 0. In addition to this, there is another this equal to this, you have to make it and solve the problem for these optimization problems. So, let us now see how to solve such type of problems in practical problems using the Hamiltonian principle formulation. So, our example is taken some, let us call, we have a resistance and we have a one capacitance is there, which is connected in parallel with an inductor. Agree? And that our problem is, this is the current flowing through the circuit I of t, which we denoted by U of t, input to the circuit, and that resistance is R, and that value let us consider is a 1, and that is the inductance. That value you consider the value, numerical value of L is equal to 1 Henry, and C is 1 farad. Agree? So, let us call current flowing through this one inductor is I L of t, and which we denoted, the current flowing through this is denoted by a variable x 1 of t. Agree? So, the voltage across the capacitor, with a V c of t, agree, that we denoted by a variable, x 2 of t, is voltage across the capacitor. So, what is our problem? The initial state x 2 of 0 is nothing but a voltage across the capacitor, which is given to 2 volt, and initial current flowing to the inductor is assumed to be, this is nothing but a current flowing to the inductor is assumed to be 0. So, our problem is to find a control input u of t, in other words I of t, such that after a finite time interval, the voltage across the capacitor and current flowing to the inductor will be 0. So, our problem is find a control law u of t such that the loss in the circuit, power wastage in the circuit will be minimum. Not only this, after a final time interval T f, the voltage across the capacitor and current flowing to the inductor must be 0. So, we now these are the our, if you can say, these are the all initial condition for the circuit or for the system. So, our problem is find the input current or input control signal u of t, which is equal to I of t, so as to waste the least possible energy in the resistor, and not only this, and bring the system state, bring the system at a time T f, at a finite time T f, you can write finite time T f, to a 0 voltage across the capacitor. Not only this, a 0 current through flowing through the inductor, through the inductor. So, now you say this is our control problem. What is the we have to optimize? We have to optimize the power loss in the resistor part is minimum, that is we have to power. So, an initial condition, state of the initial condition of the inductor, current flowing through the inductor is 0 and voltage across the capacitor is 2. We have to find a control signal I of t or u of t such that the circuit attains the in a finite time the voltage across the capacitor is 0, current flowing in the inductor is 0. Not only that, during this finite time the power wastage in the resistance part will be as minimum as possible, means minimum. So, this is our problem statement. So, now in order to put this problem in the framework of what is called optimization of dynamic optimization problem, then we have to write the dynamic equation of this system into x dot is equal to f of x, which is a function of x t, u t, comma t. So, let us see how we can make it that one. So, we know by basic what is called this voltage across this one, voltage across this one is same as the voltage across the inductor is same as voltage across the capacitor. So, I can write by the L d I dt, L d L current flowing through this one of t dt is equal to V L is equal to V c of t, and V c is we have considered voltage across the capacitor with a variable x 2 of t, and current flowing through the inductor, I L of t is a variable x 1 of t. So, we can write L x 1 dot of t is equal to x 2 of t divided by L. Agree? Since our case we have considered L is equal to 1 Henry, C is equal to micro 1 farad, then we can write this is nothing but a x 2 of t. So, this value is 1. So, that is let us call equation number 1. Another equation we can write it, if you see this one, current flowing to the capacitor is nothing but a, by using the KCL law, Kirchhoff's current law at this point, I L I of t is equal to I L plus I C. So, I C current will be is equal to I C current flowing to the capacitor. You can write it here is current flowing to the capacitor I C of t, agree, I C of t. So, I C of t I can write it total current minus current flowing to the inductor. So, you know the current flowing capacitor is equal to C dV voltage across the capacitor with respect to time is the current flowing to the capacitor is equal to I of t minus that I L of t, and I of t is u of t input and I L is x 1 of t. Now, this is nothing but a B c is x 2. So, it is nothing but a x 2 dot of t is equal to u of t by c minus x 1 of t by c is equal to, since c is equal to 1 farad, then it is u of t minus x 1 of t. So, that is equation number 2. So, combining equation number 1 and 2, I can write x 1 dot of t, x 2 dot of t is equal to, this is 0, 1, then it will be a minus 1, 0, that is x 1 of t, x 2 of t, then plus 1, 0, then 1, just this equation and this equation we club together, this and this we club together and writing like this way. Agree? So, this equal to this into u, and this is a very well known structure of state space representation of a system. That is, we can write it, this is nothing but a x dot, this is x dot of t is equal to A is a matrix, this matrix is A, or you write A x of t, A is a constant matrix plus B u of t, which we can write it is nothing but a function of x of t, u of t, comma t. So, it is a general form we are writing, x dot is equal to function of this, and this f is a 2 dimensional, because it has a 2 equations are there, x 1 dot, x 2 dot. So, this system dynamic equation, this is a system, this is described into a what is called a state space form, or in other words this we can represent into a second order differential equation, which can be converted into a 2 first order differential equation, which is written into this form. So, let us call this is equation number 3. Agree? So, now what is our performance index? If you see what is our performance index according to our problem, that our performance index is Pi, performance index is, you have to minimize the loss in the resistive part of the circuit, that means I square into R. So, I have a, that means I square into R of dt over a finite time interval t 0 to t is equal to 0 and t is equal to T f, and this is we have to minimize. But we have already discussed in our static optimization problem that if the performance index, if you add something constant term, or you multiply by performance index by a constant term or divide by constant term, the optimal point does not change, but optimal value may change it, but optimal point at which the function has a optimum value, that will not change. So, we can make it, this is a divided by 2, half. Why we made it, it is half, we will explain this thing later, because this portion, because when you do the what is called our derivation, everything we have shown, there will be a 2 will come and 2 and half will be cancelled, otherwise the 2 will be carried out through the our formulation, that is why this half. But our optimal point at which this will be optimal, that will not change it, but optimal value function of the optimal value may change it. So, let us see the how to solve this one. So, if you recollect our that numerical example we have considered, let us consider equation number 1. So, we rewrite the equations as per our statement of the problem. So, we have the equation, if you see x 1 dot is equal to, we got it x 2 dot, let us call this is 1, this set of equation are 1, x 2 dot of t is equal to minus x 1 of t plus u of t. This is equation number 1 and 2 combinedly, now I am rewriting is equation number 1, and the performance index, and the performance index, that is what will be as j is equal to T 0 to T f half, this half I square, I is our u t, u square of t, r is 1, this value r is 1. So, dt, agree, which this is, you say r value is what, so it will be that one. So, which we can write it as x of T f, the boundary condition, and this is T f, there is no boundary condition. So, this part practically it is 0 plus T 0 to T f, T 0 is to T f, T 0 is 0, our T f, then our half u square dt. Okay. So, this quantity is now according to our problem, it is nothing but a integrand of the integral cost function integrand. So, it is a function of x t, u t and x t u t and comma t. So, this part I can write it that one. So, so our problem is that if you see determine a control law or signal that will drive the system from an initial state from an initial state x 1 of 0 is equal to 0, means current flowing through the inductor is 0 from this condition, and current voltage across the capacitor is a 2 volt. Okay. So, this is the initial condition of the system states. So, our job is derive a control law u such that initial condition atho will come to the final state x 1 T f and x 2 T f is 0 in a finite time, and as well as it will minimize this performance index. So, that is our problem. So, to the final state, from an initial state to the final state, x 1 T f is equal to x 2 T f is equal to 0 in minimum waste of energy or minimum control effort, minimum control effort. What is the minimum control effort? Suppose you have a resistance, that resistance. What is the, if current is flowing through the resistance, what is this our energy involved? I square R into T, and in our case R is 1. So, it is I square means U square. So, it is nothing but a multi input case is nothing but a U transpose U indicates the control effort. So, that control effort we have to minimize for a fixed value of resistance. So, this is the control effort to minimize, or the energy wastage in the circuit is minimized. This is this one. Second point is obtain the system time response for this control law, for this optimal control law. So, this you see our problem is given the system minimize the performance index in such a way, minimize the performance index, that is this, by selecting U control effort, you minimize this performance, and this performance index minimization means the minimum what is called waste in the loss in the resistive part will be minimized. So, we have framework, this we can write it, if you see this we can write it x dot of t is equal to f of x of t, u of t and t. So, we have now made it in general framework, x dot is equal to this, and our performance index is terminal condition. In our present case, terminal condition is 0 plus that integral cost function. This is the integral cost function and this is the terminal cost. We have framework. So, we will now apply that whatever the method we have discussed earlier using the Hamiltonian function. So, this now we are in a position to solve this problem using the Hamiltonian function. So, if you see the solution, and our objective is clear, to bring the state from initial state to final state in a finite time interval, agree, as well as it should minimize the performance index, that P I, agree, and subject to that conditions. So, our solution is first you form Hamiltonian matrix, Hamiltonian equation or function. So, h of this is equal to half u square of t plus lambda transpose f of x of t u of t, and this is equal to half u square of t plus lambda. Lambda is a, because the dimension of the state is 2, lambda is at lambda 1 of t, lambda 2 of t, multiplied by x dot of t is what? You just see when you put into a vector form this, then we can write it, this is nothing but a x 2 of t minus x 1 of t plus u of t. This is our f of x. Agree this. So, if you simplify this one, this into this multiply, it is a half u square of t plus lambda 1 into x 2 of t plus lambda 2 into this one, means minus lambda 2 into x 1 plus lambda 2 of t into u of t. So, this is our Hamiltonian function. So, once we know the Hamiltonian function, so this is our equation number 1, and let us call this is our equation number 2, that one, equation number 2. So, and this is equation number 3, the Hamiltonian function is equation number 3. So, immediately we can find out what is called the del h del u of t. So, this is equal to 0. What is del h del u? U term is involved here and here. So, this is twice u t is equal to lambda t. So, if you see this one, u of t plus lambda of t is equal to 0, u of t is equal to minus lambda 2 of t. So, once you do this one, or you can write in step or first step is 1 is form Hamiltonian function. Second step is your step is form del h del u. Third step, that what is the algorithm we have written, according to that we are following. Third step, using the value of this h of this, we are writing, use the value of u of t, replace u of t by lambda of t, then it will come half, this will be a half, replace u of t by minus lambda 2 of t. So, this will be lambda 2 square, lambda 2 t square, then plus lambda 1 of t x 2 of t, just h I am writing h expression what we got it, we have written it, and replace u of t by lambda minus lambda of t only. Then your minus lambda 2 of t x 1 of t minus that is lambda 2 square of t. So, if you simplify this and this, it will be a minus lambda 2 square of t, other terms as it is. So, I am writing other terms as it is, lambda 2 of t x 1 of t. So, this is, let us call this is equation number 4, this is equation number 5 I am writing. Now, what is the way to do it? We have to find out what is called del h, del lambda, del h, del x, both the state and co-state equation we can write it now. So, next is your step 4, del h, del lambda is equal to del lambda means what? If you see this one is nothing but a that one del h, del lambda 1, del h, del lambda 2, that two things, and this I can write it del h, del lambda 1, lambda 1 term is involved here, is nothing but a first term, this term is nothing but a x 2, del h, del lambda 1 is a x 2. This is the x 2 and this will be a, and this is we are differentiate with respect to lambda 2. So, it will be a minus lambda 2 twice lambda 2, 2 cancel, this will lambda 2 and this will be a x 1. So, this will be a minus x 1 minus lambda 1 lambda 2 of t, this one, just this value I am getting. We know lambda h by lambda dot is equal to x dot, that expression. So, we can write it that is this we are differentiating with respect to lambda 2. So, this will be minus, that is you see this is a minus sign, agree, and so this equal to what? This equal to we know that will be a your x 1 dot of t, x 2 dot of t. Look, this expression del h del lambda is equal to x dot. What is x dot? X 1 dot is and x 2 dot. I am now writing the value of delta, del h is nothing but a del h lambda 1 whose value is x 2, del h del lambda whose value is minus x 1, this is the minus, note this is the minus x 1 minus lambda 2. So, from there I can write it that one equation, that if you see I can write it x 1 dot is equal to, see this one, this equation x 1 dot is equal to x 2 of t, x 1 dot is equal to x 2 of t, let us call this equation is 6. Then second equation you see x 2 dot is equal to minus lambda x 1 of t minus lambda 2 of t. So, I can write it x 2 dot of t is equal to minus x 1 of t minus lambda 2 of t, that is equation number 7. So, this is the state equation, that now co-state equation, lambda h of dot x of x dot is equal to minus lambda dot of t. So, this is nothing but a del h del x 1 of t del h del x 2 of t, this one is equal to minus lambda 1 dot lambda 2 dot. So, this now you differentiate this thing with respect to that del h, that is what we got it here. What is this expression? That you differentiate this with respect to x 1 del h del x 1. So, x 1 term is there, only it will be a lambda 2. So, I can write it this equal is equal to your lambda 2, because you have differentiate with respect to lambda 1 lambda x 1, then if you are differentiate del h del x 1, you see del h del x 1. So, if you differentiate this one, it will be lambda 2 minus lambda 2. So, it is a, you can write it minus dot lambda 1 is equal to minus lambda 2 of t. Therefore, lambda 1 of t dot is equal to lambda 2 of t. This is. So, let us call this equation is 8. Similarly, from this equation, this is I am writing from this equation, this is from this equation differentiating h with respect to x 2, x 2 is involved here only x 2. So, lambda 1 of t if you differentiate with respect to x t. So, this is a lambda 2 dot of t is equal to minus lambda 1 of t. So, let us call this is equation number 9. Just these two equation, co-state equation we written. So, this is one equation and this is another equation we got it. So, we got it co-state equation. Now, we see from equation what we can do it from equation 8 and 9. From equation 8 and 9, if you differentiate this thing with respect to t, lambda 2 dot is equal to minus lambda 1 dot. Okay. So, from 8 and 9, lambda 2 dot we are differentiate once again with respect to time t is equal to minus lambda 1 dot of t. Now, see lambda 1 dot of t is lambda 2 of t. So, I am writing is nothing but a minus lambda 2 of t. So, it is something like a x dot is equal to minus x. So, it is a homogeneous equation. The solution of this one we can get it like this way. This is equal to alpha 1 e to the power of j t and alpha 2 e to the power of minus j t, this one. And this if you take the Euler's formula, all these things, you will get alpha 1 plus alpha 2 cos t plus j alpha 1 minus alpha 2 sin t. That means, e to the power j t is cos t plus j sin t. Here is cos t minus j sin t. Then simplify, you will get it this one. Let us call this equation is equation number 10. Okay. So, this is the solution of x lambda t. Now, you see note at time t is equal to 0, lambda here lambda 2 of 0 is equal to alpha 1 plus alpha 2 sin t is 0. Agree? This we got it. Let us call this is equation number 11. Agree? Note lambda 2 dot this again from here is equal to alpha 1 plus alpha 2. Alpha 1 alpha 2 is the constant which will can solve the characteristics equation. If you solve it, you will get it that this roots and this is the associate with the that is a constant. This is the constant, real constant number, maybe complex also. So, this is a alpha 2 dot is equal to alpha 1 plus alpha 2. Differentiation of this one is minus sin t plus j alpha 1 minus alpha 2 cos t. So, at time t is equal to 0, then you can write it lambda 2 dot of 0, this value we can write it lambda 2 dot of 0 is equal to alpha 1 plus alpha 2, this is 0 into 0 plus j alpha 1 minus alpha 2 this. Agree? So, this we got it that lambda 2 is lambda dot is this and we know lambda dot is what? Lambda dot t is equal to lambda dot t is equal to lambda 2 dot t is equal to minus lambda 1 t. So, I can write it minus lambda 1 t t is equal to j alpha 1 minus alpha 2, because this we know, since we know from 9, if you see from equation 9, from 9 that lambda 2 dot of t is equal to 2 dot of t is equal to minus lambda 1 of t. From that you got it lambda 1 0. So, so this expression we got it. Now, from 10 and 12, let us call this is the equation number is 12. From 10 to 12, from 10 to 12, what we can write it? From 10 to 12, we have say 10, 11 and 12. What we can get it? Lambda 2 of t from 10, lambda 2 of t is equal to, now see this we got it, this value what is lambda 1 plus lambda 2 in this value is lambda 2 of 0. So, this equal to lambda 2 of 0, then it is cos t as it is, but j lambda 1 j alpha 1 minus alpha 2 j alpha 1 minus lambda 1 minus lambda 1 of 0. So, this is cos t minus lambda 1 of 0 sin t. So, let us call this is equation number 13, and if you differentiate this one, h root is equal to lambda 2 of 0 minus sin t minus lambda 1 of 0 cos t. So, this values you know minus lambda 1 of t is equal to lambda 2 of 0 minus sin t and minus lambda 1 of 0 cos t. So, let us call equation number 14. So, I know the expression for lambda 2, I know the expression for lambda 1. Okay, this is the final expression for lambda 1 and lambda 2. But still I do not know what is the lambda 2 and lambda 2 0 all these things. If I know, then our what is Lagrange multiplier description is known, provided if I know lambda 1 of 0, lambda 2 of 0. So, from equation 6 and 7, you see the from equation 6 and 7, I recollect this one from 6 and 7, what you can write it x double dot, if differentiate this thing with respect to once again with respect to time, the x double dot is equal to x 2 dot, and express the x 2 dot with this one, replace x 2 dot by this one. So, I am writing now from 6 and 7 x 1 dot, 6 is x 1 dot. So, I am differentiating with respect to time once again is equal to x 2 dot, and x 2 dot is equal to minus x 1 of t plus u of t, and what is u of t? Minus lambda of t. So, it is u of t which is nothing but a, this is minus lambda of t. So, this will be a minus x 1 of t minus lambda 2 of t. Agree? So, so what is the our minus x 1 of t? What is lambda 2 of t? Just now we have got the expression for lambda 2 of t. You see the expression for lambda 2 of t, we got it here, sorry here. So, I will write it this expression, that expression is what? Minus lambda 2 of 0 cos t minus lambda 1 of 0 sin t. So, that I am writing, this I am writing from equation 13. Okay. So, replace the lambda 2 value by this one from equation 13 this. So, this if you look at this expression here, that x 1 double dot is equal to minus x 1 of t sum quantity is there. This whole thing I can consider, this whole thing I can consider as an input to the systems. That whole thing I can consider as if it is a input to the system, or differential equation is a forcing function, or it is a forcing function to the differential equation, forcing function to the differential equation. Okay. So, now this solution you can easily find out, because it is something like S double dot is equal to minus, or you bring it this one, x 1 double dot is equal to plus x 1 of t plus some forcing function. So, that solution one can find out easily, that one. So, let us call the solution of x 1 of t. Therefore, x 1 of t is equal to twice sin t. So, I leave this thing as an exercise to check the solution of that one is this, that second order differential equation, what we got it, lambda 1 of t sin of t minus t cos of t minus half lambda 2 of 0 t sin of t. So, we have done up to equation 14. This equation let us call, this is the equation of 15. So, our control law is nothing but a u of t is nothing but a minus lambda 2 of t. So, lambda 2 of t, if you know this one, we can find out the control law. Once we find out the control law, then we can find out the trajectory x of t. But here lambda 2 of 0, lambda 2 of lambda 1 of 0 is unknown. This is unknown. This is unknown. So, you have to find out these values. Then only lambda 2 is there. Once lambda 2 is there, then we can find out the control law. So, our trajectory is this one. Still, if you see that lambda 1 0, lambda 2 0 is unknown to us, and not only this, that this, and another thing you see x 2, this is our x 1 t, and we know from the dynamic equation x 1 dot of t is equal to x 2 of t, that is called from 16. This is from dynamic equation of the system, equation of the system. See equation number 1. So, x 1 dot, if you differentiate this one, x 1 dot is equal to x 2, which equal to this right hand side, if you differentiate this one, twice cos t plus half lambda 1 of 0. This one will be what? Sin cos t minus t. This one we have to differentiate that thing with respect to this. So, first is differentiate this one, let us call this will be then cos t, then unchanged minus sin t, agree, minus sin t, then this part minus half lambda 2 of 0, then sin t, then plus t cos t. Agree? See, just I have differentiated this one, and that is nothing but our x 2. So, our x 2 expression, therefore, our x 2 expression is nothing but a twice cos t plus half lambda 1 0. Then if you simplify that one, then what will come? Just I am simplifying these things, then lambda 1 t half lambda 1 0 t sin t minus half lambda 2 0 sin t, because this and this are cancelled. So, it will be a minus, this is minus, this is minus, minus minus plus. So, it will be half lambda 2 0 t sin t, and this is as it is, this part will be as it is here reproduced, sin t plus t cos t. Now, this trajectory I mentioned is u of t is from the condition we got minus lambda 2 of t, and lambda 2 of t is a function of, if you see, is a function of that our lambda 1 of 0, lambda 2 of 0. Again, once I know lambda 1 0, lambda 2 0, then lambda t is known. Here also you see x 1 t is a function, we need the information of lambda 1 of 0 and lambda 2 of 0. Agree? Then we can find out x t trajectory, optimal trajectory, x 2 trajectory, which will control input as well as x 1 t, x 2 combinedly, it will minimize the our performance index. Agree? That consider. So, applying now what is our left with us? Only boundary condition. From the boundary condition, we have to find out x 1 lambda 1 of 0, lambda 2 of 0 boundary condition, and in the boundary condition our T f is free. What is fixed? That x T f is fixed, means both the state, that current flowing through the inductor, current voltage across the capacitor must go to the 0. So, applying the given end point boundary condition, we get at t is equal to T f x 1 T f current flowing in the inductor, this is x 2 T f current voltage across the capacitor is 0. This is the, we know our boundary condition. So, if you apply the now boundary conditions, this one, if you recollect this, our boundary condition H del S x of t, this delta t whole thing, put t is equal to T f delta T f plus del S x t of t del x of t minus lambda of t whole, t is equal to T f transpose, this transpose, just say the boundary condition multiplied by this, multiplied by, that is I am writing multiplied by u delta x f is equal to 0. Now, this delta x f, if you see that delta x f is in our case is 0. So, only this is not equal to 0. So, our condition is delta dot, and this, since we do not have any terminal condition, this part is 0, no terminal condition according to our problem statement. So, this you find out t is equal to T f, this is equal to 0. So, this is our boundary condition that finally boils down to these equations. So, from equation 5, what is the equation 5? You just say that our basic Hamiltonian equation, Hamiltonian function, this equation from equation 5, I will write it t is equal to T f. So, from equation 5, put t is equal to, from 5 t is equal to T f, then your half minus lambda square of T f, agree, that is half lambda square of T f this is what this equation you see, half lambda square of T f, then lambda 1 T f x 2 T f minus lambda 2 T f then x 1 T f is equal to 0. So, what I did it here, you see h of this, put the value t is equal to T f is equal to 0. So, this one. So, this equation is 0 because terminal what is called final state variable values is 0, this is 0. So, only this one. So, this one will lambda 2 T f is equal to 0. So, from 13, so we have given from 13, you see equation number 13, refer to equation number 13, that one, lambda 2 of t is this one. Okay. So, from equation 13, t is equal to T f. So, lambda 2 T f is equal to lambda 0, lambda 2 0. See this equation, lambda t is equal to T f, this lambda 2 0 cos t minus lambda 1 0 sin T f, t is equal to T f is T f. This quantity is 0, just we got it, this is 0, t is 0. So, it is a, we can say this is lambda 2 0 cos T f minus lambda 1 0 sin T f, this is equal to 0, that is agree. So, let us call this is equation number, what is the equation number we got last equation number 9, 16, then you give it this equation number is 17. Agree? This x2 expression, that x2 expression, what we got it, x2 expression twice cos of same, that is you give it 17 because this will refer 17, this you give it 18. Agree? Now, see this one, this is unknown, this is unknown and T f is unknown. Okay. 3 unknowns are there, we need 3 equation, which 3 equation are your so, I can put it now that this is 18 from 15 to 15 and 17, t is equal to T f at t is equal to T f, 15 is that one you see 15 and 17 is that one, 15 and 17, 15 is this one, 17 is that one. In this expression t is equal to T f you put it, t is equal to T f, t is equal to T f. So, left hand side is 0, left hand side 0. So, you have a 3 unknowns are there and 3 equations are there, but that 3 equations are non-linear. So, you have to solve it to get the final value of lambda of 0, lambda 1 of 0, lambda 2 of 0 and T f, and that will give you the total picture of what is called what is the optimal control law as well as what is the optimal trajectory, which will minimize the performance index of that one. So, a part of this one is left. So, I will continue next class, okay, this one. So, I will stop it here now.